rate of dissolving solids. This picture of a solid ionic compound will look familiar. Let's let a cation be a small black sphere and an anion be a larger white sphere. So here's a fraction of a unit cell in a simple cubic solid ionic compound. Notice each cation is surrounded by anions, and you could extend it outward so that this cation in the bottom right sees one in front, one behind, one to the right, one to the left, one above, and one below. And it's the same deal for the anions. They see only cations, which we see if we extend it outward over here. But in any case, in order for this to dissolve, your solvent, water, has to get in between the ions. And so our water molecule has partial negative charge on the oxygen and partial positive on the hydrogens. It's capable of disrupting those interactions, but in order to do that, it must collide. And the harder and the more frequently those water molecules can collide with that piece of solid, the more they can disrupt the ion-ion interactions and start making ion dipole interactions. And we should say that before dissolution, the intermolecular force present in the ionic compound is ion-ion interactions. That present in the solvent is hydrogen bonds. And we want to make ion dipole interaction. So here's a hydrated cation. Note that the water molecules have their oxygen end, which is negative, pointing towards the cation, which is positive. So we see ion dipole interactions here. And here is a hydrated anion with the negative charge of the anion pointing towards the hydrogens on the waters, which is positive. So again, that's ion dipole in the hydrated ions. Right, and we already said that the water is the solvent, and then the solid ionic compound is the solute, and the hydrated ions represent the solution. Here's an overview of the energetics of the solution process. We start out at zero energy with a liquid solvent and a solid solute. We then put in however much energy is needed to disrupt the solvent-solvent interactions. In this case, that represents overcoming hydrogen bonds. Once we've done that, our solvent is now in the gas phase, and of course we still have a solid solute. Then we got to disrupt the interactions in the solute by putting in more energy. Now at this point, we have a gaseous solvent plus a gaseous solute. Now this is an artificial point on the graph, but it helps if we break this down into steps. Now we need to form, the solute-solute interactions that we disrupted. Those were ion-ion interactions. Now we're going to go over here and form the solute-solvent interactions. And to do that, we're going to take energy out, or rather, doing so liberates energy. So we'll go with blue. Right, and this represents the ion dipole interactions in the hydrated ions. So now, in this case, our solution, our aqueous ionic compound, is lower in energy than where we started, and so this arrow here represents a negative heat of solution. Oh boy. So heat is given off in this process. Now, if the blue arrow were shorter, we could end up with a positive delta H of solution. Anything that we can do to increase the rate of collisions between solute and solvent molecules will make the solute dissolve faster. If we grind up our particles, you get smaller particles, and smaller particles have more surface area as a group. Say I have a cube whose dimensions are 2 centimeters on a side. Then the surface area equals the area of a face times 6, because there's 6 faces to a cube. So 6 times 4, that's 24 square centimeters. Now imagine I take that cube and I divide it in half in the vertical axis, and I divide it in half in the horizontal axis. Oh, and I also have to divide it like this. Making these divisions, I now have 8 smaller cubes with a dimension of 1 centimeter. So, the surface area of each face is 1 square centimeter. Each cube has 6 faces for 6 square centimeters per cube, and then since there are 8 of them, I have 6 times 8 equals 48 square centimeters. So, the smaller particles have more surface area. More surface area means more collisions per second, and that means faster dissolution. Something else I can manipulate is temperature. At higher temperature, particles have higher kinetic energy. In other words, they're vibrating faster. That means the collisions are both more frequent and more forceful. So no matter what, things will dissolve faster at a higher temperature. Finally, we have stirring. If you've ever put sugar in iced tea, you know that it'll dissolve faster the more you stir it. This is because you locally get a high concentration of solute in solution surrounding the solid. So stirring brings fresh solvent in contact with solute and disturbs that concentration gradient. Again, it makes your collisions between solvent and solute more frequent and increases the rate of dissolution.